and now it at Exeter. So Geoff, I let you speak about moist geophysical fluid dynamics.
Thank you. Thank you, Freddie, and thank you for inviting me to this. Yeah, I'm mainly going to talk about a Madden-Julian oscillation in particular, and trying to understand it, trying to distill it. Ted Johnson just mentioned that he was going to try and hear all about the MGO, but I'm just going to tell you something about the MGO. So it's sort of what I hope is as it were, the truth and nothing but the truth, but not the whole truth, if that makes sense. And oops, okay. And this is what the MJO is. This is taken from some figures which appear both on the NOAA website and the Met Office website. The MJO has been described in this paper by Fuchs and Raymond that it has been and still remains a holy grail, that the basic physical processes are still unknown. I think that's a little bit bleak, because I think we do know something about it. But this is basically what the structure is. And you see here's a map of the Southwest Pacific Ocean and the Indian Ocean. And what seems to happen every couple of months or so is that a storm develops over the Indian Ocean, which is rather intense and rather big, and it draws air in from either side, and so you get a lot of intense rainfall and clouds and excites gravity waves, and there's all sorts of things. And then, perhaps to everyone's surprise, or it would be to people's surprise if they didn't know that this was going to happen, this storm moves steadily eastwards at about 5 meters per second, maintaining its structure, and eventually it goes all the way across the Atlantic, all the way across the Pacific, and finally decays just west of South America. So that's what it is. One would like to know why it forms, why it maintains itself, and most of all, why it moves eastwards at about 5 meters per second. So, and that's been the object of study for 40 years or so, ever since it was first discovered. And when I gave a seminar about this at Harvard, somebody said to me, you know, Geoff, you're not allowed to explain the MJO because it's, you know, it's meant to be a mystery. So, you know, we have to keep it that way. Here's another view of the MJO. Here we're looking at the outgoing long-wave radiation. Blue is less outgoing long-wave radiation, so it's cold, basically looking at where it is cloudiness. Here along the x-axis is longitude, and here is time going up. In 1983, 1984, we didn't see any particular MJO activity, but here you can see, if you can see my, can you see the laser pointer here? You see the blue patches going up and to the right. They are this cloudiness, this storm activity moving eastwards at about 5 meters per second. Here's another couple of examples. The MJO comes in various shapes and sizes. Sometimes, that's in the top left-hand corner, it doesn't exist at all. Sometimes it moves a little bit slower, like in the bottom left-hand corner at about 3 or 4 meters per second. And here, sometimes we have MJOs moving pretty quickly at 5 or 6 meters per second. But the common feature is that a lot of cloudiness, a lot of storm activity, a lot of precipitation, and it's all moving eastwards at a few meters per second. Why doesn't it move westwards, one might well ask. Well, we start to get some hints of what might be going on and what makes the east-west symmetry by looking at the composite structure, which you can see here. This is the structure from many MJOs which have been patched together. The top plot shows the geopotential height at 850 hectopascals, which is near the surface. The bottom plot shows a similar plot at 200 hectopascals, which is near the troposphere, near the tropopause. The green arrows are sort of, or the green lines and the red lines are my hand-drawn lines over the top of the contour, so you can see the pattern a little bit better. And this blue patch here is where we have lots of precipitation, is the center of the MJO. And what you can see are two things. First, it has a relatively simple vertical structure, in that the structure at 850 hectopascals is almost in a sense, the mirror image of what it is at 200 hectopascals. Just the signs have changed. And secondly, you can see a dipole structure on either side of where the intense precipitation is. So here's the precipitation around here. And here you can see the motion converging towards the center of precipitation. So you can see sort of almost straight away why it might maintain itself, because once you have this precipitation, the air converges both from the east and from the west, bringing moisture with it, causing there to be more precipitation. Okay, so here's the sort of the summary of what I've just said. The dipole structure just slightly to the west of where the clouds are, which is the blue. It's got a fairly simple vertical structure. It's the first baroclinic mode. Then this pattern moves slowly eastwards at a few meters per second. I should say that this is a composite of many MJOs. If you actually look to see instantaneously at a particular picture, it's just a real mess. You can see lots of isolated convection, and you don't see this pattern nearly as well. Now, if you've taken a class in geophysical fluid dynamics, you'll know that this pattern, which I've reproduced on the right, looks very much like a classical pattern in geophysical fluid dynamics known as the Matsuno-Gill pattern. And I plotted the analytic solution for the total pressure here on the top left panel. Basically, that pattern results from some concentrated heating here in the bottom left panel. So if we put a bunch of heating here, when Gill first did this calculation, he imagined that the heating was coming from a sea surface temperature anomaly. It doesn't really matter where it comes from, but if you put a chunk of heating here, what happens is that you get this resulting pattern in the pressure field. And this resulting pattern in the pressure field, well, it comes from two main effects. One, east of the pattern, you actually have a Kelvin wave, and it may be damped because of frictional effects or radiative damping. So here we're just showing the stationary pattern associated with that heating. So this lobe here extending eastwards is actually a stationary Kelvin wave, and these two lobes on either side, which are slightly west of the heating, are actually stationary Rossby waves. So if you put a heating in here, and the bottom left panel, you will fairly generically, this pattern will fairly generically emerge just the result of a Kelvin wave to the east and two Rossby waves on either side, slightly off the equator and displaced slightly to the west. And you can see these arrows showing showing the flow of air which is converging towards the heating. Now, this is all dry fluid dynamics, but it does suggest that the Madden-Julian oscillation, which you can see in the right-hand plots, is pretty similar to actually a propagating Matsuno-Gill pattern. So the Matsuno-Gill pattern is a stationary pattern due to stationary heating. But this entire pattern then moves eastwards across the equator, maintaining its structure. So it's really suggested what we have here is a propagating Matsuno-Gill pattern.
Geoff, may I ask you a question? So before you have shown the baroclinic structure. So often, if I remember well, the Matsuno-Gill pattern is studied in a barotropic model. Am I correct? Or?
Yes and no. It is a baroclinic structure, but it's a. Let me just go back to here. It's a single vertical mode. So it is primarily a baroclinic structure because it's its phase goes to 180 degrees phase change in the vertical, but because it is dominated by a single baroclinic mode, you can simulate it with, well, basically with the shallow water equations with a single layer in the vertical. So that single layer represents the baroclinic mode, if that makes sense. So you only need a single layer, but that layer is the baroclinic mode. And you get something rather different, actually, if the heating is centered off the equator. So here is the, if you will, the Gill pattern centered off the equator, here a little bit off the equator and here even more off the equator. But if, for example, you initially got heating off the equator, you wouldn't actually get the convergence toward the heating because now you have a Coriolis effect and the flow flows around the heating rather than toward it. So you can begin to see why the Madden-Julian oscillation is centered at the equator, because that's where the heating would give you a convergence. And the other thing you get in the MJO, perhaps which led to people realizing that it was some kind of structure different from an ordinary wave, is if you do a so-called Wheeler-Collardis diagram in which you decompose the disturbance into its time frequency components here on the vertical axis and its spatial components, the zonal wave number here on the x-axis. These solid black lines are actually the dispersion relationship for Rossby waves, here, Kelvin wave here, and just ordinary gravity waves up at the top. The actual disturbance, which one finds when you analyze the observations, is composed of Rossby waves and Kelvin waves, but here's the MJO down here, fairly close to the origin, and it doesn't exist on the Kelvin wave dispersion relationship. It's telling us it's a larger scale and slower than a Kelvin wave. So it is something different that we can't explain just from purely linear dynamics. Okay, so we're going off in search of this Holy Grail. And let me give you a few key observations. That all that precipitation arising in the MJO, all the moisture which gives rise to it actually comes from convergence, not from local evaporation. So you're drawing a lot of air in from either side to provide that precipitation. And if you look at where the heating is coming from in the thermodynamic equation, it's not coming from the sea surface. It's not a sea surface temperature anomaly. which was the original motivation for the gill pattern, but it's actually coming from condensational heating. And here's just a few references of previous work on it. A lot of the work that I'm going to talk about, in a sense, is a development of this early work by Raymond and Fuchs, and they coined the phrase moisture mode, implying that there's somehow an interaction between the moisture and the large-scale circulation, and that it wouldn't exist in the absence of moisture. It's rather difficult, actually, and one of the puzzles has been that general circulation models have actually had very mixed success in reproducing an MJO, and many of them, including the UM, don't really do very well at all. There have been some successes with extremely high resolution models. This paper by Miura et al., I think, was a model with something like a 4 kilometer resolution model. And what I'll talk about is actually using the moist shallow water equations, which is a development of really of this paper by Bouchou et al. The et al. Is Vladimir Zeitlin. Their motivation was more towards vortices and hurricanes, but I'll use those equations for the MJO. And the tenet that I'm going to argue is that the MJO is a form of convective aggregation on the beta plane, not necessarily self-aggregation, if you will. It's not just maintained by itself, but it's because it's on the beta plane that it will aggregate. But it is moisture driven, and the beta plane, which is just the variation of the Coriolis effect with the latitude, that enhances the aggregation and actually makes it more likely to happen. And the beta plane also provides you an east-west asymmetry, and it's that which makes it propagate eastwards. And I guess my goal, since I'm just that kind of person, is to find out what is not needed rather than what is needed. So I always think, in my mind, I understand something when I know what you don't need to explain it. We're looking for the bare minimum of what's going on. And I'm going to focus mainly on the propagation mechanism. And actually, in a sense, coming back to Freddie's question, I'm going to use the moist shallow water equations, which are just a single layer. But it turns out that if you take the primitive equations with vertical stratification and you expand the vertical structure in terms of vertical modes, that the first bioclinic mode, the first mode, gives you the shallow water equations, more or less. And so that's what we'll use. So if you do have this relatively simple vertical structure, which I will posit, you can model them with the shallow water equations. But then I'll add a moisture variable to it, which is where all the fun begins. I won't constrain the horizontal structure, and I won't parameterize convection except in a rather basic way. And I'm going to try and then analyze and hopefully understand the system. So here are the moist shallow water equations I'm going to use. The top two equations, which are the equations in blue, are just the regular shallow water equations, which should be familiar to all of you. Momentum equation, the Coriolis term, the pressure term, and a frictional term. Second equation is the height equation, which in the shallow water equation kind of doubles as a thermodynamic equation and a mass continuity equation. And we can regard H really is a proxy for temperature, or in the way I've written it, it's the negative of temperature. So smaller h corresponds to a higher temperature. And this term on the far right-hand side of the second equation will be some kind of a radiative relaxation of the height equation to some specified height. So that would just be our radiative forcing. But then I'm going to add these terms in red. So here, this L times C is a condensational heating. And that comes from the addition of a tracer, which represents moisture. Q is the level of humidity. So here's a conservation equation for humidity. And then it's forced by evaporation, and it also condenses. So imagining, just going back to this earlier picture, that this layer of shallow water lies over a saturated surface. So then there's evaporation from the surface. And also then when the condensation exceeds a certain value, then it rains. And it rains quite quickly, so that the value of Q never exceeds Qsat. So Qsat is just a saturation value, and that's determined by a Clausius-Clapeyron-like equation. And rather approximately, Clausius-Clapeyron tells us that the saturation vapor pressure varies exponentially with temperature, which I've represented by this equation here. There's a negative here, H is a negative temperature in my system. But, you know, Q is being advected around by the velocity. It may converge or whatever. And then if Q reaches or exceeds the saturation value, it immediately rains. It condenses, which is the term here. And that condensation is then a source in the thermodynamic equation. So this is essentially what I mean by most geophysical fluid dynamics. We're not trying to simulate the full equations in all their glory with multiple layers and complicated radiation scheme and complicated saturation scheme and complicated boundary layer. We've really simplified the system greatly to the momentum equation, thermodynamic equation in the shallow water system, and to that we've added this moist tracer, which condenses and provides a heat source. Okay, so that's my system. And what happens when I try and integrate it? Well, weird and wonderful things happen when I try to integrate it. And here's just a snapshot. And it's a snapshot of the movie, which I'll hopefully show in the next slide. Typically, movies only work about 60% of the time in presentations. But hopefully it will work. But you're going to, if it does work, you'll see lots of pictures like, see a movie like this, and I will just go through it. So these are snapshots of results from a numerical simulation. This is the height field, and this is the precipitation field, these dots here. So you can see at this particular time that it's raining here, and it's producing a pattern which actually looks a little bit like this gill pattern. It's got these lobes on either side off the equator, slightly west of the precipitation, and then this long leading lobe, which is a Kelvin wave. And then this is at time 44 days, and at time 55 days, we see that the disturbance has actually moved eastwards quite a lot. I guess I should go down. It goes from here to here. from 44 days to 49 days, it's moved down to here. And it's moved even further east at 55 days. So we do get a steady eastward propagation at about 5 meters per second. Let me hopefully show you the movie. So we're just going to start the system from rest. We're just going to integrate these equations. We're going to start them from rest. We have a saturated surface, and we're going to provide a perturbation, which you will see. That perturbation will saturate the atmosphere. It will condense. That condense will provide a heat source to the system, which will cause convergence, more saturation, more of a heat source, and so on. And in this first movie, I'm going to show what happens without any rotation at all, not even an F-plane, just the shallow water equations. And let's hope it works. Oh, there it goes. So let me just start from the beginning. So I'm going to apply a perturbation here at about x equals minus 0.25, y equals 0. It will rain there. That will provide a perturbation. We'll see a front propagating out from the initial system. That will provide more rain, and the system will become totally self-sustaining. Okay, so let's go. These are gravity waves propagating out. There's a front of rain propagating out. You can see lots and lots of gravity waves all over the place in the left-hand plot. Blotches of rain in the right-hand plot, moving around slightly at random. It's sort of like a game of life in a sense. And you think it's all going to die out. But then it never actually dies out. It just keeps on going. It becomes a self-propagating system, and it's an excitable system, some people would call this, with gravity waves and rainfall just keeping on going. But of course, it doesn't look anything like the MJO. So this time, I'm actually going to put it on in a rotating system on the beta plane, so the Coriolis parameter varies with y. And now this y-axis actually means something. The equator is at y equals 0. And the initial perturbation is here off the equator. So let's see what happens now. So it looks almost the same. We're starting to see near the equator it's starting to organize itself, and here now you can see the rainfall near the equator here. You can see this self-organized pattern, which once it organized itself is starting to move steadily eastwards at a few meters per second. And then it's going to exit the system here and come back on the left. And you can see what's happening. The system is just an excitable one, and you can see on the left, especially if you have a little bit of imagination, that it's generating a gill-like pattern. But you'll see it as it comes around again. But there's a Kelvin mode eastwards of where the precipitation is, with two Rossby-like modes on either side of the equator. Okay, so turns out that the speed of it is dependent upon things like how much latent heat release there is, what the evaporation rate is, and so on. And if there's no evaporation at all, of course, you don't get any. You don't get an MJO. And it also turns out that if you mimic the conditions in the Pacific a little bit by making the sea surface temperature larger, or the evaporation rate larger in the eastern part of the domain, the storm will always form here and then move off eastwards to where it's cold, and you get less evaporation here, and they will die out. And then it will form again here, again move off to the right. Somewhat like reality. Now, it turns out also you can, and this is unpublished work done by a student at Oxford, Neil Lewis, who's now back in Exeter, but we configured a fairly simple general circulation model, and we can see similar kinds of patterns here. You can see an MJ over here moving off to the right with the same kind of precipitation pattern in this general circulation model. So what's going on, and can we further simplify it? But I guess what is going on is encapsulated in this diagram. So what we are supposing is that we have convection here. Let's suppose initially, for whatever reason, we have a pattern of convection here, which is where this dark blue oval is. Convection releases heat. It generates this gill pattern. So you have a Kelvin lobe off here to the east, and you have a couple of Boswell lobes off here on either side of it. What happens then is that the air is drawn towards the region of convection. Warm, moist air is particularly drawn in from the east. Somewhat cooler, drier air is drawn in off the equator towards this. So the moisture is drawn in towards where the convection is, and it provides more convection, and it sustains itself. But it also turns out that the moisture convergence is slightly to the east of where the initial convection pattern was. So if the moisture convergence is slightly to the east of that pattern, then the new source, the new thermodynamic source, will be slightly east of where the convection pattern is. So you'll get some more convection here at a slightly later date in this paler blue oval. And then the whole system will propagate eastwards. So why is it the equator? Let me just summarize where we're at. Why is it at the equator? It's because it's only at the equator that convection will actually give you convergence where the convection initially exists. If you're off the equator, the Coriolis effect will move the air around rather than giving you convergence towards it. Why is it eastwards? It's because the convection produces convergence, as we've said, but it leads to more convection, which is slightly to the east of the initial disturbance, and I'll come to that again in the next few slides. So it self-perpetuates itself, but it moves eastwards all of the time. Various things which some of the sort of professional tropical meteorologists are concerned about are whether things like wishy, which is wind-induced evaporation, are important, or westward trade winds are important. And in my model, it turns out that they help, but they're not essential. And just to bring in a couple of caveats here, that I haven't really addressed the mechanism of maintenance fully. It's going to be a very complicated thing. I mean, even in the shallow water system, it's complicated. Never mind if you have a full system. I mean, the convection itself is complicated. Turns out that it's even complicated in the moist shallow water system, that the excitability is a little bit delicate. It depends slightly on how you configure the relaxation timescale, the time step, and the way that the condensation actually occurs. And there's a little exchange in the literature between myself and Davidson and Haynes, which you can read about in the quarterly journal. Okay, but let's try and simplify the system still more, and suppose that a priori the system is a gill-like system. And this gill pattern is going to advect moisture around, and it's going to give us right convergence and condensation, and that will produce a heat source and so on. And does the pattern move? So can we further distill it? So what I'm going to suppose is a priori we have a gill pattern in the pressure field, and I'm going to allow that to move around moisture, which is evaporating and condensing. And here, for example, is just the pattern of moisture which the gill pattern will produce. So if I take this gill pattern, the saturated specific humidity will have a very similar shape to it, because it's really just an exponential of the temperature. So it's going to have the same shape, but it won't be exactly the same, because the saturated specific humidity is not linearly proportional to the pressure, it's proportional to an exponential of pressure. And that's going to actually make an important difference. And you can start to see that difference here. So here, I've just taken these exact fields, taken the analytic gill model, and this is the saturated specific humidity, which is also calculated analytically. And then I calculate what the velocity convergence is and what the moisture convergence is, of these two patterns. So the velocity convergence is the divergence of the velocity in the gill pattern, and it looks like this. The moisture convergence, which is the divergence of UQ, looks like this, which is almost the same, but it's not exactly the same, and it's slightly to the east of the velocity convergence. You can see that most clearly in these line plots in the bottom plot here. The velocity convergence is this red line here, but the moisture convergence, which is this dashed blue line, is almost the same, but it's slightly offset to the east. So you can see now why the whole thing might move to the east, because if the moisture convergence is off to the east of the initial pattern, the new pattern, which is going to form just a little bit later, is going to be to the east of where the initial velocity convergence was. That will provide a new source, and so on. And here's a similar plot again. Just essentially, this is just a numerical integration of the moisture shallow water equations, but with the gill pattern built in, and now with an additional field for the condensation. So, okay, the red line again is the red line is the convergence of the velocity, and the blue line is the condensation field. And here we have it again, slightly different parameters. The red line is the convergence of the velocity. The dashed blue line is the condensation. It's always slightly to the east of where the initial convergence is. And here we see it one more time. I'm looking at the convergence of the moisture here in this left-hand plot. These arrows are U times Q and V times Q. and the blue contours are its convergence. Here I'm looking at just U and V and the humidity, again in blue. But the red cross is where the convergence is maximum of the moisture field, and the blue cross and the red cross here is where the convergence occurs for the velocity field itself. So it's the moisture convergence is to the east of the velocity convergence, and the reason for that is simply because you've got a lot of moisture coming in from the east along this Kelvin mode. The air itself, apart from converging here, tends to detour round and come back around these Kelvin modes, around these Rossby modes. So the air is coming in from both sides. The air coming in from the east, and some of it diverges and comes round and back again. And so the air which is converging from the west tends to be a bit drier because some of it has come from off the equator. So it's come around from here. So it's drier because it's come from, it's drier because it's colder. So the moisture convergence is slightly to the east of the velocity convergence. And that's a very generic result. You know, if you have a gill pattern and if you have moisture. And it doesn't matter, I should say, if we have precisely the gill pattern. Here I'm just looking at variations on a theme, if you will. The actual gill solution is a particular analytic solution with a particular source field. But if we do variations of that by changing the distribution of condensation, we will always find that the condensation in these various different patterns, which is the red line, is always slightly to the east of where the heat source is. Okay, so here's just another little picture, that's just to give you a schematic of what's going on. Here's the gill pattern. Well, let me do it here. Here's the gill pattern as being drawn in from the east, circulating around and coming back again. But the moistening, the actual heat source is round about here. You can see my little red dot going up and down, but the convergence of moisture is a little bit to the east of that. And here, if you will, is an elevation rather than a plan view. The moisture is coming in up on the ground or near the ground. Here's the center of the pattern. Rainfall is to the east of that, and off it moves to the east. We can actually make a little toy model of all of that, just to see what, you know, we're sort of making a toy model of a toy model, if you will, you know, layering down our toy models. Let me just, but the key features are simply that the condensational heat source is to the east of the center of the pattern. And the pattern is then drawn towards that heat source, which produces another condensational heat source east of the pattern. So here's a little toy model for those who like ordinary differential equations, with two variables, x sub phi, position of the center of the pattern, and x sub c, which is the position of the condensation. So the condensation provides a heat source which generates the pattern. So the position of the pattern is relaxed towards the center of the condensation. That's what this equation is. Okay. But the moisture is drawn to a position which is offset to the east of the pattern. So that's what this equation represents. The position of the condensation is drawn to a position, it's relaxed to a position which is east of the center of the pattern itself. Okay, with these two relaxation rates, K1 and K2. And that actually has, you can solve these equations, and the solution is this. That the position of the condensation is some initial condition times these various constants times time. Therefore, it's moving off to the east at a speed determined by what these parameters are, which are the rate of the relaxation of the pattern itself and of the condensation. And one can simplify that a little bit more, because the pressure field, which is in a sense this X sub phi field, that can adjust much more quickly than the moisture itself, because the pressure field will adjust on a gravity wave speed, whereas the moisture source itself can only be moved around advectively. So in the equations I showed, that means that K1 is much bigger than K2, K1 being the relaxation rate of the pressure field. Then you can simplify these equations. If K1 is bigger than K2, K1 actually cancels out. So that the speed is given by this expression, which is kind of important. And this is finally the distillation, if you will, of the MJO. And it tells us what its speed is proportional to. That it's actually proportional to the offset of the center of the pattern and the condensation. Because if there's no offset at all, you won't get any movement. But it's also proportional to this K2, which is the rate at which the condensation can move. It's the rate of advection of the moisture field itself. It's the rate at which the moisture field can move towards the center of the heating. So that's an advective rate, because moisture is moved advectively, not a gravity wave speed. So perhaps the new result here is that the MJO speed of propagation is an advective one. It's not a gravity wave speed. It's the speed at which moisture can actually be moved around. And it turns out that, in fact, I put a question here, does the shallow water model respect this result? It does. That the displacement, this is the displacement of the natural location of the condensation in the toy model. And it does respect that result that the propagation speed is proportional to this displacement here. Okay, let me just summarize the results of this and then make a few general remarks about moist geophysical fluids. So I'm arguing that the MJO is a form of convective aggregation, if you will, but not self-aggregation in the sense that it needs an external agent to give you that aggregation, and that external agent is the beta plane. It enhances the aggregation, makes it occur at the equator, and it makes the disturbance propagate eastward. Our speed is an advective one related to the actual fluid speed, not a gravity wave speed. And it depends upon the location of the condensation relative to the center of the pattern. And it's all really about the interaction between the condensational heating and the large scale pattern. So it's a two-way interaction. between the condensational heating and the large-scale pattern. You can make a lot of objections to this, of course. You know, as you can in a sense to any theory in geophysical fluid dynamics, which tries to represent a real, you know, a real process. The atmosphere is not a shallow water model. You know, well, we know that. But the MJO does have a simple vertical structure. And the moisture is all in the lower atmosphere. So I'm not too worried about that. Of course, there'll be lots of details because of the lack of an explicit boundary layer and so on. Condensation is not determined by moisture convergence alone. Again, I agree, but nonetheless, the convergence of moisture is the main source of precipitation in the Madden-Julian oscillation. This third objection is one that some people, professional tropical meteorologists, like to make. The convection primarily determines the lapse rate and not the heating, which is a long-standing argument between people who believe in quasi-equilibrium versus conditional instability of the second kind. And I don't want to get into this argument. It's a sort of a technical one and a slightly arcane one, I think. But observations do show that the condensational heating is the main component of the thermodynamic budget in an MJO event. So the condensational is providing the driving for the MJO pattern. I've sidestepped the features, the details of the instability that perpetuates the process. I regard that as a sort of a feature of what I've done, not a bug. It's always good if you can avoid a difficulty, and so on. And various issues, again, for professional meteorologists to do with wind-induced evaporation and cloud radiative effects are almost certainly quantitatively important in the process, but not necessarily qualitatively important. So actually, I think probably it's best to stop here and leave it there and see if there are any questions from the audience.
Yes, thanks a lot, Geoff. So I think we can clap. So do we have a question from the audience?
I would have a question.
Yes.
Yeah. Well, first of all, thanks for the talk, Geoff. It was very interesting. I have a question. You kind of touched a bit on towards the end, and that has to do with the Matsuno gill. You actually have this gravity wave response, and especially the Kelvin wave is very fast, which of course determine also how you choose your settings. And now you introduce this heating, which kind of works against the propagation of the gravity wave in a sense. So I was just wondering, is it just a fortunate tuning of the parameters that it just works out to be look so nice, or do you think it would be a general rearrangement of the atmosphere that it would just do that itself?
I think it kind of does it itself. Let me see if I can go back to a. Can you see this slide okay?
Yeah, it's okay.
I mean, here's a sort of a snapshot of some of the shallow water results. And you know, if you play the movie, you know, you do see Kelvin waves and gravity waves and so on, and they're all in the mix. So they all exist. It's not like we're, damping the actual transient waves, but they're somehow superimposed upon the stationary Matsuno-Gill response, which is what is producing the propagation, of the MJO. So in a sense, we have the MJO structure with its, Kelvin lobe and its two Rossby lobes on either side. You don't really see it so much in the instantaneous field. It's only so much when you make a composite that you see it rather nicely. So I'm not, filtering those out. But it's sort of the stationary pattern which is underlying it and causing it to move in a systematic way.
So, yeah, it makes sense. I was just wondering, so for example, if you would now change the fluid depth and thereby kind of the gravity wave phase speed, would that automatically also imply that you would change the behavior of the convection in a way that everything kind of falls into the same place, or is this kind of tuning important?
There's a little bit of, there is some kind of tuning involved. In a sense, to get the right speed and so on. So, I mean, for example, I can find out my, at the end I say, why don't all GCMs get MJOs? And I think the key thing is, perhaps to answer your question, the mechanism is quote unquote simple, but the actual emergence of an MJO does depend somewhat sensitively on the parameters. So, if convection is triggered too close to the existing convection, the pattern won't move. If it's triggered too far east of the existing convection, the pattern moves too fast and it breaks up. So therefore, it is going to depend somewhat sensitively on your convective parameterization. And if you don't get that right, you might just get spots of convection and no organization. So I say here, we do expect a model MJO to depend somewhat sensitively on convective parameterizations. It needs to be somehow just right. And perhaps that's why a lot of GCMs don't get it. And it seems to be a little bit of a black art in tuning them. So yeah, I'm sort of agreeing with you in a way that we perhaps are a little bit lucky in that the real atmosphere gets one, and some GCMs seem to get it and some don't.
Thanks.
Ted has a question, does he?
Yes, you might have answered already. Oh, have I got my volume on? Yes.
I can hear you loud.
You might have answered it already, Geoff. But what vaguely is going on with the energy in this? You're radiating your energy in the Kelvin waves and the Rossby waves. Where are you mainly getting it from?
It's mainly coming from here, this term, which is the condensational heating. So we are losing energy, as you say, in the Kelvin waves and Rossby waves. I mean, well, the domain is finite, so they are coming back. They're not going off to infinity necessarily. But the energy source for in the momentum and thermodynamic equations is ultimately the condensational term.
And you have an infinite amount of that.
And there's in a sense an infinite amount of that because it's all stored in the moist surface at the bottom. So so if I look at the energy, if I do a time series of energy of the system, once it's settled down, it's sort of in a statistical steady state. I mean, it's bouncing up and down quite a bit. And it's not, exactly conserved, but it is in a statistically steady state. And without this condensational term, the whole thing, would die out eventually.
That if you switch that off, it would run down.
I switch that off, it would die out. Yeah, exactly.
So, Geoff, in the description of the data at the beginning, it seems that the phenomenon is periodic, is more or less periodic. Is this true?
Yeah.
It seems.
Semi-periodic or quasi-periodic or something like that. And well, you can also see it actually in the simulations.
Well, in the simulation, it's because you have a doubly periodic domain, so you.
Yeah, but in this simulation, which I think sort of reflects reality, I have a domain which I make it warm here and cold over here. So it's warm in the west and cold in the east. And because it's warm there, that's where all the evaporation occurs, right here. And then the disturbance moves off eastwards, and then it dies out here. Now, after a certain amount of time has passed, a new one will emerge here, and then the whole process starts all over again. So the new one emerges, 40 days or a couple of months after the old one, when the system has, recharged itself, if you will, because once you have an MJO here and it moves off, it's too dry here for another one to form. So you need to build up the moisture again, and that takes, a month or two. So that's where the periodicity comes from. It's not like a periodic wave, but it needs to sort of recharge itself. And it, sometimes people call it the 40-day oscillation or the 40 to 60-day oscillation. So that's, I think, where it is coming from, but it's not a periodic wave.
And so you mean that this period that comes from this recharge has nothing to do with the speed of the phenomenon?
It's not got a whole lot to do with the speed. Yeah, that's what I'm saying. It's except in an indirect way, that they will both be determined by the availability of moisture. So the availability of moisture will determine the speed at which it moves and also the speed at which it can reform itself. But the periodicity is not directly related to the speed. No.
Do we have more questions? So thanks a lot, Geoff. This was a really very nice talk, very clear, very interesting.
Okay, thank you.
Thank you.
I'll try to see you next time.
Okay.
Thanks again, Geoff.
Next
Very
time.
interesting.
Yeah.